Hello, my name is Nitesh and I'm part of Team 24. And our project is audio mapping using LiDAR to assist the visually impaired. For this project, I worked with Ben, Irene, Alan, and Jason, and we all worked under the assistance of Dr. Gert Cauwenberghs and Akshay in the Integrated Systems Neuroengineering Lab. So in 2020, it was estimated that there are 43.3 million blind individuals worldwide, an increase from 36 million in 2015. And so with the growing number of blind individuals, it's ever more important to have an effective mobility aid.
The major problem we are tackling is that current solutions for visually impaired individuals, like white canes or guide dogs, lack the ability to provide spatial awareness and depth perception. These solutions are well designed for detecting obstacles in close range that are low to the ground, like curbs or trash cans. However, they fall short in detecting moving obstacles, distant obstacles, and elevated objects above the user's waist. Having a device that can track the distance of an object over a longer range with a flexible range of motion would allow users to detect a variety of obstacles and provide them with an artificial depth perception.
In this project, we had three main goals. The first is that the device is able to detect objects. The second is that we create an audio feedback system that is both intuitive and distinct. And the third is that the device is able to be used in obstacle avoidance.
To meet these objectives, we introduce AudiioSiight, a wearable solution to aid in navigation for the visually impaired. To detect objects, AudiioSiight makes use of LiDAR, which stands for Light Detection and Ranging. As you can see in Figure 2, each LiDAR has two lenses. One lens is used to send infrared light out, which when it hits an object will reflect back to the receiving lens. The LiDAR then measures the time it takes for the light to return back to the sensor and uses it to calculate the distance between the object and the sensor. Our device makes use of two of these devices, for which we use the TF Luna single-point LiDAR because of their low cost and small size for a wearable device. We use two LiDARs so that the user can determine the direction of the nearest object. Each LiDAR provides a single distance value of the object in front of it, which is processed by our Arduino Trinket microcontroller and sent to an off-board computer via an RC transmitter. The circuit schematic can be seen in Figure 1. The off-board computer receives the data with another Arduino and converts the processed distances to sound using MATLAB and plays the appropriate audio feedback to the user. The sound is played through to the user through a pair of Bluetooth stereo headphones, for which the sound through each ear can be individually controlled. In Figure 2, we see the finished device, which is being worn in Figure 3 along with the Bluetooth headphones.
With regards to our software feedback protocol, as Irene mentioned, we want our feedback to be intuitive and distinct. And we accomplish this with our double coding strategy, which utilizes different pitches and beeping speeds to convey information about the surrounding environment in an intuitive manner. With the different pitches, a high-pitched sound would convey information about something that's close to the user, and a low-pitched sound would convey information about something that's far. Likewise, a fast beeping speed would be something close to the user, and a slow beeping speed would be something far from the user. And so these modalities in conjunction can make it easy for the user to understand, as it's the same information in two different mediums. In Figure 4, we see the whole system design of this feedback protocol. It starts with the LiDAR camera, which takes a distance value in centimeters, and this value is binned in 1 meter increments. So the first meter, 0 to 1 meters, was the first bin. The second bin is 1 to 2 meters, and so on up to 5 meters. Beyond 5 meters, the information will no longer be as useful, as it can be confusing to the user. These bin values are all assigned a pitch and a beeping speed, with again, a bin that is closer to you will be something that is fast beeping and high pitch, and something far from you will be a slow beep, low pitch sound. And we utilize this design in our directional feedback system, as seen in the Figure 5. In scenario 1, we see the instance of two different bins. The left-hand and right-hand LiDAR both get a distance value, and these values are both binned. The left-hand LiDAR getting a bin of 3 and the right hand of 4. These values are compared, and we emphasize the third bin as it's closer to the user. And so the left-hand side will produce audio and the right-hand side will be silence. And so it tells the user there's something closer to you on the left, so you should move to the right. In scenario 2, we see the instance where the bins are the same. And so in this instance, because there's an obstacle on both sides, we want to tell there's something in front of you. And so audio would be output in both ears.
As Irene mentioned, we had 3 primary objectives for our device. We designed 3 tests so that we could test each of these objectives. The first objective was to accurately detect obstacles. In order to do this, our LiDAR sensor needed to be sufficiently accurate. To test this, we designed a testing apparatus that involved positioning a large cardboard target and measured distances between 0.5 meter and 5.5 meters from our LiDAR. LiDAR sensor measurements were recorded and compared to actual distance measurements to determine percent error. We concluded that our sensors were accurate to within 2% of the actual distance, which was sufficient for our prototype given the 1 meter bin sizes. The second objective we tested was the intuitiveness of our audio feedback system. We designed a testing protocol that involved playing 30 random audio cues, each associated with one of our distance bins, and recording the subject guesses. Subjects were told whether or not they guessed correctly in order to facilitate learning. Data was recorded for 6 subjects with approximately 3 trials per subject. It is important to note that these audio cues were played randomly, but in practice, we would expect smooth transitions between consecutive bins. For example, it would go from bin 1 to bin 2 instead of bin 1 to bin 4. Because of this, we would expect our audio system to be even more intuitive in practice. The third objective we tested was for obstacle avoidance. To do this, we designed a cardboard obstacle course for our subjects to navigate. We recorded the number of obstacle collisions and the total runtime for each trial. Our subjects consisted of 4 volunteers that each participated in 1 control run where the user was blindfolded and 4 device runs. For the device runs, users were still blindfolded, but were able to use our device to help them. So here we have a demonstration of our obstacle course testing. So you can see that we used obstacles of various shapes and sizes, and these obstacles were rearranged between trials so the subjects couldn't memorize the course or start to understand the layout. We also got a sample of the audio feedback. Our actual device uses stereo headphones, so we get directional feedback that you may not be able to hear here.
Results from audio cue testing to meet our second objective of creating intuitive and distinct audio cues yielded about 90% accuracy. In figure 6, the blue diagonal denotes when the users correctly guessed the bin that the audio cues belong to, while everything else outside the diagonal that is yellow shows incorrect guesses. These incorrect guesses are visually summarized in the pie chart in figure 7. We can see that bin 1 and 5 had small slices, showing that users did not make as many mistakes when identifying these bins, unlike the middle bins 2, 3, 4, which have bigger slices and show that more errors were made when identifying these bins. As Jason mentioned earlier, in practice, we expect the results to be better because in reality, we don't expect bins to jump from 1 to 5 since objects usually approach or go away incrementally. It is important that we randomly play the tones to test the user and so that we could also test the distinguishability of the cues. Ideally, the minute that the device is turned on, the user should be able to just hear 1 audio cue and be able to approximate the distance to the detected object without hearing any other audio cues.
The results of our obstacle testing show that our device significantly reduced obstacle collisions when compared to a blindfolded control. The left figure highlights this, showing that obstacle collisions were reduced from about 10 collisions per run for our control to about 4 collisions per run for our device runs. While this preliminary testing is promising, Further testing on visually impaired individuals with training in current aids is necessary to determine if our device can actually improve performance. The right figure shows average times for each trial across all subjects. We see that there appears to be a decreasing trend, indicating that user runtimes improve as they get accustomed to using the device. However, the large standard deviations between users gives us little statistical confidence. More testing is required to improve confidence that our device is in fact intuitive. We didn't include the control run here since we expected those to be much faster, as users were blindfolded and had no means of avoiding obstacles. So they would run into an obstacle and then just move around it.
In our project, we were able to obtain accurate distance data from our LiDAR cameras efficiently enough to provide real-time feedback for the user to navigate around obstacles. From our preliminary testing, we have also found that audio cues we have designed are intuitive and distinct enough for a user to recognize differences in our feedback and comprehend what they mean. These differences in feedback allowed our test subjects to greatly improve their performance in avoiding obstacles. If we had more time and resources, we would conduct more testing and expand our test subject group to include people who are actually visually impaired to get a more accurate measure of how our end user would use the device. They will be able to test our product in tandem with whatever assistance they currently use to see if it adds any significant value to their spatial awareness. Variable bin sizes may also be a good route to explore, like different modes to suit different environments, such as one where you'd want to focus on finer details. We would also hope to use better components to improve the build quality of our device, potentially including onboard processing and rechargeable batteries. We could also add supplementary features like haptic feedback.
We'd like to express our gratitude and appreciation to Dr. Gert Cauwenberghs and Akshay from the Integrated Systems Neuroengineering Lab for their guidance and wisdom, providing us with helpful insight on our considerations for software and hardware for our project. Additionally, we'd like to thank our professor, Dr. Bruce Wheeler, and our TAs, Cicely Penatil and Brian Nguyen, for their support in our Beng 187 senior design course. Thank you.